Let's continue our discussion by looking at another 3-transistor current source configuration, the Wilson current source. And so as you can see here, again, we have Q1, Q2, and Q3. The main difference is now our Q3 is over here on the right side of the circuit as opposed to the left with our basic 3-transistor current source. Notice another difference here in the circuit is we have Iref explicitly defined here as a current. The reason I've done this is to be consistent with the textbook, but we can also just have a resistor in place of that current source, and then we could pretty easily, if we want, do a KVL path. So we just start down here at the bottom, go through VBE for Q2, go through VBE for Q3, go through our resistor, and then we're at V+. So you also see that with just a resistor. For whatever reason, the textbook has just decided to use Iref here. Okay, so again, like we've done last time, we're going to assume that we have identical transistors. So we're going to assume identical transistors. And so what that means is that we have VBE1 equals VBE2. And so we can see that just from down here. We know that these are both equal to VBE. Those are the same. And so what that means, based on our transistor IV equations, we know that IB1 is going to be equal to IB2, and if IB1 is equal to IB2 and the transistors are matched, meaning they have the same beta, that means our IC1 is also equal to our IC2. And now the main difference, since we pulled this Q3 over to the right side, is now we have roughly the same current levels in all transistors, which means all of the betas are going to be the same, roughly. So similar current levels in Q1, Q2, and Q3 means we're going to have the same beta for all three of them now. Okay, and so let's label some currents and voltages on here in order to facilitate our discussion. So, of course, what we're going to be interested in ultimately is this output current that's going to our output as I have labeled here. And so this is going to be our collector current for Q3. So IC3, which we're also going to call I out. On the other side here, we have our emitter current IE3. And notice our emitter current IE3 is still providing these base currents. So we have IE3 being broken into two parts. Part of it is coming down this way. And so that is ultimately going to become our two base currents for IB1 and IB2. And it's also splitting into this collector current IC2. Okay, so if we come over to the left side of the circuit, we see that this Iref is being split into our IB3 and our IC1. And so we can say that these three transistors have similar current levels. Of course, now because our IE3, we're just taking a small part of that to serve our base currents IB1 and IB2, as opposed to last time where our IE3 was only supplying current for our IB1 and IB2. But now it's also splitting into this IC2, which is going to be roughly the same value. Okay, so let's start by applying our KCL, our Kirchhoff's current law. And so we're going to be looking at the left side first. So we're going to look at this node here. And so our approach is going to be similar to what we saw with our basic 3-transistor current source. We're kind of going to, it's going to seem like we're just kind of writing up random equations, but ultimately we're going to sort of pull them all together in order to relate our I out to our Iref. So at that first node, when we do KCL, we have Iref equals IC1 plus IB3. Well, we said these are matched transistors, so that means IC1 is equal to IC2. And our IB3 we can write as IC3 over beta because, again, I've implicitly just assumed that these transistors are operating in our forward active mode. So we're going to call that equation 1. Okay, so now we can also do a KCL right here at this point, and we see that our IE3 is splitting into 3 different currents. It's splitting into our IC2 and our IB1 and our IB2. So we can simplify this a little bit as well. We're going to leave our IC2 alone, but we can say because these are matched transistors, Up here we said they have the same base current, so let's just say this is 2IB2. And we can even take that a little further because again we can relate IB and IC through beta if it's in forward active. So let's say this is equal to IC2 times the quantity of 1 plus 2 over beta. So that's going to be our equation 2. And again, we're using the same beta now because we're saying the current level in these three transistors is roughly the same. So now, by definition from our transistor properties, we can say that our emitter current, IE3, is equal to our collector current, IC3, plus our base current, IB3. Okay, again, we're going to simplify that and say this is IC3 times the quantity of 1 plus 1 over beta. So essentially the same thing we just did with that previous equation. And let's call that equation 3. Okay, so now what we're going to do is let's start. So we have all the information here we need. We just need to rearrange it to relate our IREF and our IC3, which remember is our I out. So we're actually going to start by rearranging this equation 2. So let's rearrange this equation 2 to solve for IC2. So we can say IC2 is equal to IE3 divided by the quantity 1 plus 2 over beta. Okay, so now what we're going to want to do is substitute our equation 3. So we're going to take our IE3, which we had here, and we're going to plug that in for IE3 in this equation right here. So what is that going to give us? Well, we're going to have IC3 times 1 plus 1 over beta divided by 1 plus 2 over beta. Now we can do some algebra and we can combine those terms in our brackets there. So we can have IC3 times in brackets. Now we're going to have beta plus, see if I can't draw a half decent beta here. So beta plus 1 divided by beta. So we basically just found a common denominator and combined these. And then in the denominator, beta plus 2 over beta. So what we see here is that our lone beta terms are going to cancel out. And we're going to be left with IC2 is equal to IC3 times beta plus 1 divided by beta plus 2. So let's call this our equation 4. Okay, so now what we're going to want to do is we're going to take this expression from equation 4 for IC2, so all of this, and we're going to take that all the way back up to equation 1. And so the idea is once we substitute that into equation 1, we're only going to have IREF and IC3. So let's see what that looks like. So if we do that, we have IREF is equal to IC3 times beta plus 1 over beta plus 2. So that's what we just substituted. That's our equation 4. And then plus IC3 over beta. And so we can go through a couple algebra steps, and I don't think I want to do that explicitly just to not spend a lot of time on these basic steps. But the algebra is in your notes, but we can rearrange this, combine these terms. Of course, we can see we can factor out an IC3 there. And if we do that and solve for our IC3, we'll get IC3 is equal to I out, which is equal to IREF in the numerator divided by 1 plus 2 over beta times 2 plus beta. And so this would be our expression relating our output current to our reference current in our Wilson current source. And so we notice that the form of this is very similar to our 3 transistor current source. Really there are only 2 differences. The first is that we have a 2 here as opposed to the 1 that we had for our 3 transistor current source. And the other difference is that this is now just beta as opposed to the beta 3 that we had previously. So note that we have the same form as our 3 transistor source. But in this case, our Wilson source is actually a little better Wilson source is better since our beta is greater than B3. Well, so since we have beta instead of B3, I should say, instead of having that special beta because we had a lower current level. And that basically means our output current is going to be closer to our reference current, but also that we're going to have less variation with beta compared to our 2 transistor current source. So that much is going to be the same as our 3 transistor current source. So less variation with beta in our output current, I should say, compared to our 2 transistor current source. Okay. One other thing that we can look at is our output resistance. So we're not going to go through deriving that. If you did want to go through the derivation, what you could do is you could replace our circuit above with the small signal equivalent circuit, and you could do analysis on that in order to get the output resistance looking in. But we notice that now our output resistance is going to be different because now we're looking into the collector of Q3, as opposed to before we were looking into the collector of Q2. So now we're looking into sort of these 2 transistors combined as opposed to just one. So what we would see is that our output resistance now is capital R naught for our output resistance is approximately equal to beta over 2 times R naught 3. And so this expression is for our output resistance for our Wilson current source, where our R naught 3 is the small signal transistor output resistance of Q3. So small signal output resistance of Q3. And so again, that's looking into the collector of Q3. So what we see is that we have a beta over 2 factor increase in our output resistance. So in output resistance, and that's compared to not only our 2 transistor current source, but also our basic 3 transistor current source. So compared to our 2 trans and 3 trans sources. So that's our 2 transistor and our 3 transistor current sources. And so ultimately, what does that mean? Well, that means that we're going to have a smaller dependence of our output current on variations in our output voltage, so to speak, that collector emitter voltage. So smaller dependence of I out on output collector voltage. And so like we looked at when we were talking about loading and the early effect, ultimately what this means is we're going to have less dependence on the load. Because as that load is changing, as load conditions are changing, that's going to oftentimes cause our collector emitter voltage in our current source to change. So here we see the smaller dependence of I out on output collector voltage, which we could also say is less dependence on load conditions. So remember, we had said from our 2 transistor current source, we're trying to improve in terms of stability of our output current with respect to beta variations and stability of our output current with respect to variations in our output voltage. So we can see with our Wilson current source, we've been able to achieve both of those.